Hello there, and welcome to Nightfall Science. Tonight, we drift gently through Einstein's theory of relativity, exploring space, time, gravity, motion, the speed of light, and why clocks can tick differently across the universe. Let your shoulders ease and let your eyes grow heavy. Spacetime has quietly shaped the cosmos for billions of years, and it will continue while you fall asleep. Let's begin. Relativity begins with a surprisingly simple idea. Motion depends on what it is measured against. A person sitting inside a smoothly moving train can appear perfectly still relative to the seat. At the same moment, that person moves rapidly relative to the ground. Both descriptions are correct. There is no contradiction. The difference comes from the frame of reference. A frame of reference is simply a way of describing positions and motion. The train provides one frame. The ground provides another. A passing car provides another. The Earth itself provides another. Physics does not require one of these frames to be the true stationary background. This idea already exists in classical mechanics. Long before Einstein, Galileo recognizes that uniform motion has a special simplicity. Imagine a ship moving smoothly across calm water. Inside a closed cabin, small experiments behave normally. A dropped object falls toward the floor. A pendulum swings. Water pours into a cup. Nothing in those simple experiments reveals whether the ship is moving steadily or resting at the dock. The laws of mechanics work the same way in both situations. This becomes known as Galilean relativity. It says that the laws of mechanics have the same form in all inertial frames. An inertial frame is one moving at constant velocity. No acceleration, no turning, no changing speed. This distinction matters. Acceleration can be detected locally. A car that suddenly speeds up pushes passengers backward against their seats. A turning vehicle produces sideways effects. A stationary elevator and an accelerating elevator do not feel identical. But constant straight-line motion is different. There is no ordinary mechanical experiment that reveals an absolute constant speed through space. This seems natural today, but it creates a deeper question. If there is no preferred state of rest, how should speeds combine? In everyday life, the answer seems obvious. Suppose a train moves at 50 kilometers per hour. A person inside walks forward at 5 kilometers per hour relative to the train. From the ground, the person moves at about 55 kilometers per hour. Velocities simply add. If the person walks backward at 5 kilometers per hour, the ground observer measures about 45. This is the Galilean rule for combining velocities. It works extremely well at ordinary speeds. Cars, trains, aircraft, thrown balls, orbiting machinery when relativistic precision is unnecessary. Nothing seems unusual. Then light enters the story. Light refuses to behave like an ordinary moving object. During the 19th century, physicists understand light as an electromagnetic wave. James Clerk Maxwell develops equations describing electricity and magnetism. These equations predict electromagnetic waves. They also predict a particular wave speed. That speed matches the measured speed of light, roughly 300,000 kilometers per second in vacuum. This is an extraordinary result. Light becomes part of electromagnetism, but waves usually travel through something. Sound waves move through air. Ocean waves move through water. Vibrations move through solids. So physicists naturally wonder what medium carries light. A hypothetical substance is proposed. It becomes known as the luminiferous ether. The ether is imagined as filling all space. Light would travel through it, much as sound travels through air. If the ether existed, it could provide something resembling an absolute frame of rest. Earth moves around the sun. The solar system moves through the galaxy. So Earth should move through this ether. That motion ought to create an ether wind. Light traveling in the direction of Earth's motion should behave slightly differently from light traveling across it. This difference might be measurable. Albert Michelson and Edward Morley perform a famous experiment designed to detect such an effect. Their instrument compares light traveling along different directions. If Earth moved through a stationary ether, the travel time should differ slightly. The interference pattern should shift when the apparatus rotates, but the expected ether effect does not appear. The result becomes one of the important clues leading toward special relativity. The old picture becomes difficult to maintain. Perhaps Earth somehow drags the ether perfectly. Perhaps objects change their dimensions while moving through it. Several ideas are explored. Then Einstein takes a different path. In 1905, he begins not by trying to preserve the ether. Instead, he takes two principles seriously. The first principle is the principle of relativity. The laws of physics are the same in every inertial frame. No inertial observer receives a special status. The second principle concerns light. The speed of light in vacuum has the same value for every inertial observer. This second statement creates the strange part. Imagine two spacecraft. One moves toward a beam of light. The other moves away from it. Ordinary velocity addition suggests they should measure different light speeds. The craft moving toward the beam might expect a larger relative speed. The craft moving away might expect a smaller one, but both measure the same value for light and vacuum. The speed of light remains c. Something else must change. That something is space and time. This is the central shift of special relativity. The speed of light does not adjust itself to preserve ordinary ideas about space and time. Instead, measurements of space and time adjust so that every inertial observer measures the same light speed. At first, this sounds almost backwards. Everyday intuition treats distance and time as fixed. Speed is distance divided by time. If different observers disagree about speed, that seems ordinary. Einstein keeps one particular speed fixed. As a result, different observers can disagree about distances and about durations. The mathematics ties these disagreements together perfectly. Relativity does not say everything is relative. That phrase is misleading. Certain quantities are invariant. The speed of light in vacuum is one. The structure of physical law is another. Later, space-time intervals provide another important invariant. Observers may disagree about how much space separates events. They may disagree about how much time passes between them, yet they agree on a deeper space-time relationship. Relativity therefore contains both relative quantities and invariant ones. The theory is not a declaration that every perspective is equally arbitrary. It is a precise set of transformation rules. To see why those rules are necessary, consider a clock made from light. Imagine two mirrors facing each other. A pulse of light travels upward, reflects, travels downward, reflects again. Each round trip marks one tick. Inside the clock's own rest frame, the light moves straight up and down. The distance is simple. The speed of light is c. So the tick interval follows directly from distance divided by c. Now imagine the entire light clock moving sideways relative to another observer. The light still travels between the mirrors, but from the outside observer's perspective, the mirrors move sideways while the light is in flight. The light therefore follows a diagonal path. The path is longer, yet the outside observer must still measure the light moving at c. The light cannot simply move faster to cover the longer diagonal path. So the outside observer concludes that each tick takes more time. The moving clock runs slowly. This is time dilation. The phrase sounds dramatic. The underlying reasoning is geometric. Same light speed, longer path, more elapsed time. A moving clock accumulates less time between the same pair of comparison events than a clock at rest in that observer's frame. This effect applies to every physical process, not only mechanical clocks. Atomic transitions, particle decays, chemical reactions, biological aging. Any process that can act as a clock follows the same relativistic timing. There is no special substance inside a clock that becomes sluggish. The entire structure of time measurements differs between frames. At ordinary speeds, this effect is tiny. A car moving along a road experiences time dilation relative to the road, but the difference is far too small to notice casually. At speeds close to the speed of light, the effect becomes large. A rapidly moving particle can survive much longer in a laboratory frame than its rest frame lifetime might suggest. This happens with muons. Muons are unstable elementary particles. They can be created high in Earth's atmosphere. When cosmic rays interact with atoms in the muon's own rest frame, its lifetime is short. Without relativity, many atmospheric muons would decay before reaching Earth's surface. But in Earth's frame, rapidly moving muons experience strong time dilation. Their internal clocks run slowly relative to laboratory clocks. many reach the ground. From the muon's own frame, the explanation looks different. The muon does not regard its own clock as slow. Its lifetime remains normal. Instead, the distance through Earth's atmosphere is shortened. This is length contraction. The same physical event receives two different but consistent descriptions. Earth says the muon's clock is slow. The muon says the atmosphere is contracted along the direction of motion. Both descriptions predict the same arrival event. This is an important pattern in relativity. Different observers tell different stories about distance and time, but they agree on events. An event is something happening at one place and one time. A flash of light, a collision, a clock reading, a particle decay. Observers may assign different coordinates to the same event, but the event itself is shared. Relativity organizes how coordinates change from one inertial frame to another. The mathematical rules are called Lorentz transformations. They replace the older Galilean transformations when speeds become relativistically important. At low speeds, Lorentz transformations reduce approximately to the familiar Galilean rules. This is why classical mechanics works so well in ordinary life. Relativity does not discard Newtonian physics. It contains Newtonian behavior as an approximation. This is a common pattern in science. A deeper theory does not usually erase an older successful one. It explains why the older theory worked within a limited range. Newtonian mechanics remains excellent for cars, buildings, most spacecraft navigation, and countless engineering problems. Special relativity becomes essential when speeds become very large or timing precision becomes extremely high. One central quantity in the Lorentz transformation is the Lorentz factor. It is usually represented by the Greek letter gamma. At low speed, gamma is almost exactly 1. Time dilation is tiny. Length contraction is tiny. Relativistic corrections nearly disappear. As velocity approaches the speed of light, gamma grows. Relativistic effects become increasingly significant. The speed of light itself acts as a boundary for ordinary matter. A massive object can approach c, but cannot be accelerated through c using finite energy. Why? Relativistic energy increases more and more rapidly as speed approaches light speed. Adding energy continues increasing the object's momentum, but each additional amount produces a smaller increase in speed. Reaching c would require an unbounded amount of energy for an object with Dungo rest mass. So the speed limit does not arise from a mechanical barrier floating in space. It arises from the geometry and energy structure of relativity. Light travels at c because photons have zero rest mass. Other massless fields or disturbances also propagate at this invariant speed in vacuum. The speed c therefore means more than the speed of one particular phenomenon. It represents the fundamental speed of causal influence in special relativity. Cause and effect cannot ordinarily propagate faster than c. This connects relativity directly to causality. If signals could move arbitrarily faster than light, different observers could disagree not only about how long events take, they could disagree about which event came first in ways that allow effects to precede their causes. Relativity protects causal order for events that can influence one another. This leads to the idea of light cones. Imagine one flash of light occurring at a single event. Light expands outward in every direction. After 1 second, it forms a sphere with a radius of 1 light second. After 2 seconds, a larger sphere. On a spacetime diagram, this expanding sphere becomes a cone. The future light cone contains every event that the original flash could potentially influence. A slower-than-light spacecraft remains inside this cone. An ordinary signal remains inside. The past light cone contains events that could have influenced the original event. Events outside both cones are separated in a different way. They are called space-like separated. No ordinary signal traveling at or below c can connect them quickly enough. This creates a deep distinction between different pairs of events. Some pairs have an absolute causal order. If one event can send a light speed or slower signal to another, every inertial observer agrees which comes first. Other pairs are too far apart in space relative to their time separation. Different observers may disagree about their temporal order. One observer says event A happens first. Another says B happens first. A third may say they happen simultaneously. This is not a contradiction, because the events cannot causally influence one another during that interval. This is the relativity of simultaneity, and it is one of the most important parts of special relativity. Consider two flashes occurring at opposite ends of a moving train. An observer standing on the platform may determine that the flashes occur simultaneously. Light from both reaches the midpoint of the platform at the same time. Now consider an observer sitting at the midpoint of the moving train. While the light travels, the train moves. The train observer moves toward one flash and away from the other, because light travels at the same speed relative to both observers. The train observer does not conclude that the light merely approached at different speeds. Instead, that observer concludes the flashes themselves did not occur simultaneously. The event toward which the train moved happened earlier in that frame. The platform observer and train observer disagree about simultaneity. Neither is mistaken. There is no universal definition of distant simultaneity shared by all inertial frames. This changes the meaning of now. In ordinary life, it feels natural to imagine one present moment stretching across the universe. Relativity does not provide such a universal present. Observers moving relative to one another divide space-time into space and time differently. Their surfaces of simultaneity tilt relative to one another. This sounds abstract, because daily speeds are tiny compared with c. The differences are normally imperceptible. Human life therefore encourages the illusion of universal simultaneity. Relativity reveals that the illusion is only an approximation. The universe is better described as space-time. Space and time are not fully independent stages. They form one combined structure. This insight becomes especially clear through the work of Hermann Minkowski. Minkowski reformulates special relativity geometrically. Instead of describing three dimensions of space evolving through a separate universal time, physics uses four-dimensional space-time. Every event receives four coordinates, three spatial, one temporal. Different observers disagree about the separation into space and time, but they agree on the space-time interval. This interval plays a role somewhat analogous to distance in ordinary geometry. In a flat plane, two people using rotated coordinate axes may assign different x and y differences between 2 points, but both agree on the actual distance between them. The coordinate components change, the geometric distance does not. Special relativity works similarly. Observers assign different spatial distances and time intervals, but the space-time interval remains invariant. This is the deeper unity, hidden underneath time dilation and length contraction. They are not separate tricks, they are consequences of viewing the same space-time geometry from different inertial frames. A moving ruler appears shortened along the direction of motion. A moving clock appears slow. Distance simultaneity changes. All three effects emerge from the same Lorentz transformation. They belong together. Length contraction is often misunderstood as an optical illusion. It is not merely how an object looks in a photograph. A photograph introduces additional complications because light from different parts of the moving object takes different times to reach the camera. True relativistic length contraction refers to a measurement. To measure the length of a moving object, the positions of its front and back must be recorded simultaneously in the measuring observer's frame. Because different observers disagree about simultaneity, they also disagree about which pair of endpoint events should be used. The resulting measured lengths differ. The object is longest in its own rest frame. This rest frame length is called proper length. Observers who see it moving measure a shorter length along the direction of motion. Again, the object does not feel compressed in its own frame. Its own ruler remains ordinary. Its own dimensions remain normal. Reciprocity creates another common puzzle. If one spacecraft sees another moving, it says the other spacecraft's clock runs slowly. But the other spacecraft also sees the first moving, so it says the first clock runs slowly. How can both be true? For observers moving inertially relative to one another, the symmetry is real. Each regards the other's moving clock as time dilated. The apparent contradiction arises only if the clocks later reunite and are compared. Reunion requires something to break the symmetry. One observer must change frames, accelerate, turn around, or follow a different space-time path. This leads to the famous twin paradox. One twin remains on Earth, Another travels at high speed and returns. The traveling twin is younger when they reunite. There is no contradiction, because the two twins follow different world lines through spacetime. The traveling twin changes inertial frames during the journey. The paths contain different amounts of proper time. The result is geometric. Just as two routes between locations can have different lengths through space, two world lines between events can contain different amounts of elapsed proper time. In relativity, the straight inertial world line between two time-like separated events maximizes proper time. This is another place where spacetime geometry differs from ordinary Euclidean intuition. The traveler's curved world line through spacetime contains less proper time. The aging difference is physical. Atomic clocks carried on aircraft confirm relativistic timing differences. Particle accelerators confirm time dilation constantly. Satellite systems account for it. Relativity is not only conceptual, it is measured. Another common confusion concerns mass. Older explanations sometimes say an object's mass increases with speed. Modern physics usually avoids this language. Instead, rest mass remains invariant. A particle has the same rest mass in every inertial frame. Its energy and momentum increase as its speed increases. This description is cleaner. The famous equation E equals mc squared refers to rest energy when written in that simple form. An object with rest mass m possesses rest energy mc squared, even when it is not moving. For a moving object, total energy also includes kinetic contributions. The full relativistic relationship connects energy, momentum, and rest mass. Energy squared equals momentum times c squared, squared appropriately, plus rest mass energy squared. For a massless particle such as a photon, the rest mass term is zero. Its energy is directly related to momentum. So photons can carry momentum despite having no rest mass. Light can exert pressure. Solar sails can use this pressure. Radiation can transfer momentum to matter. Relativity therefore changes the relationship among mass, energy, and momentum. Mass is one form of energy content. Energy contributes to inertia. A hot object contains slightly more mass than the same object after it cools because the thermal energy contributes to the total mass of the system. A compressed spring has slightly more mass than the relaxed spring. A charged battery has slightly more mass than the discharged battery. The differences are usually tiny, but the principle is universal. Energy gravitates too, which becomes important later in general relativity. Special relativity itself does not describe gravity. That comes later. The 1905 theory focuses on inertial frames, uniform motion, light, space, time, energy, momentum. It assumes space-time is flat. Einstein then spends years trying to extend these ideas to accelerated motion and gravity. That journey leads to general relativity. But special relativity already changes the basic stage on which physics happens. There is no absolute rest. There is no universal simultaneity. Clocks do not all accumulate time at the same rate. Lengths depend on relative motion. Massive objects cannot reach the invariant speed c, and space and time belong to one space-time geometry. These ideas can seem separate when learned one by one, but they come from a small foundation. The laws of physics have the same form in every inertial frame. The speed of light in vacuum is the same for every inertial observer. Everything else follows from making those two principles coexist. Time dilation is not added as an extra rule. Length contraction is not added separately. The relativity of simultaneity is not an independent curiosity. They are different faces of the same geometry. The speed of light remains fixed, so space and time adjust together. This is the quiet core of special relativity. A train, a clock, a beam of light, and the realization that no observer moving steadily through the universe owns the true frame of rest. The universe does not provide one preferred cosmic platform. Instead, inertial observers carry their own rulers and clocks. Their measurements differ, but the laws connecting those measurements remain exact. And beneath those differences sits one shared structure: space-time. In the next part, the ideas of time dilation, length contraction, simultaneity, and the twin paradox will be explored more deeply, showing how apparently contradictory measurements become consistent when every observer's space-time path is considered carefully. The strange effects of special relativity all begin with one simple fact. Every inertial observer measures the same speed of light in vacuum. That single statement forces space and time to behave differently from ordinary intuition. Time dilation, length contraction, the relativity of simultaneity, and the twin paradox are not separate mysteries. They are different consequences of the same geometry. It helps to begin with time dilation. Imagine two identical clocks. One remains in a laboratory, the other travels past at high speed. Each clock works perfectly. Each measures time normally in its own rest frame. Yet the laboratory observer measures the moving clock as ticking more slowly. This does not mean the moving clock is damaged. Its gears do not resist motion. Its atoms do not become tired. The effect belongs to time itself. Any physical process used as a clock shows the same behavior. A radioactive particle decays more slowly when moving rapidly relative to the laboratory. An atomic clock accumulates less time. A biological organism would age less. Every process follows the same relativistic timing. This universality is important. If only mechanical clocks slowed, the effect could be blamed on the mechanism. If only atoms slowed, perhaps atomic physics would be responsible. But every ideal clock agrees. Relativity changes how elapsed time is measured. The quantity measured by a clock moving with an object is called proper time. Proper time is one of the most useful ideas in relativity. Suppose two events happen at the same location according to one observer. For example, a clock begins a journey and later returns to the same place. The time measured by the clock following the journey is its proper time. Different paths through space-time can contain different amounts of proper time. This sounds unusual only because everyday experience encourages the idea that time is universal. In space-time, elapsed time behaves more like a geometric property of a path. Different routes can contain different amounts. The famous light clock example makes this visible. A pulse of light moves between two mirrors. In the clock's rest frame, the pulse travels vertically. One journey upward and downward forms a tick. For an observer watching the entire clock move sideways, the light follows a diagonal route. That route is longer. The light still travels at exactly c, so more time must pass between ticks according to the outside observer. The amount of time dilation is determined by the Lorentz factor. At low velocities, the Lorentz factor is extremely close to 1. The difference becomes almost invisible. At half the speed of light, relativistic effects become noticeable. At 90% of light speed, they become much stronger. At 99%, stronger again. Approaching light speed makes the factor grow dramatically. The relationship is non-linear. This is why daily motion gives almost no intuition for relativity. Walking, driving, flying, even orbiting Earth occurs at speeds tiny compared with c. Human experience occupies the gentle corner of relativistic physics. In that corner, Newtonian ideas appear exact. Only precise instruments reveal the difference. Atomic clocks have done exactly that. Place accurate clocks on aircraft, fly them around Earth, bring them back. Their readings differ slightly from clocks that follow different paths. Both speed and gravity contribute. The differences are tiny, but measurable. Modern satellite navigation depends on similar corrections. Without relativity, clocks and satellites would drift relative to clocks on Earth. Position calculations would gradually become inaccurate. Relativity therefore operates quietly inside technologies used every day. The dramatic examples involving near-light-speed spacecraft are extensions of effects already measured close to home. Particle accelerators provide even clearer demonstrations. Unstable particles moving at relativistic speeds survive longer in the laboratory frame. The particle itself does not experience an unusually long lifetime. Its own proper lifetime remains unchanged. The laboratory measures its clock as dilated. Muon experiments provide a particularly intuitive example. Muons created in the upper atmosphere have short rest frame lifetimes. Many move close to the speed of light. From Earth's frame, their internal clocks run slowly. This allows many of them to reach the surface before decaying. From the muon's frame, nothing unusual happens to its lifetime. Instead, Earth's atmosphere is length contracted. The distance to the ground becomes shorter. Both descriptions predict the same physical result. The muon reaches the detector. This example reveals an important principle. Observers can disagree about space and time while agreeing about events. Earth and the muon disagree about the journey's duration. They disagree about the thickness of the atmosphere, but they agree that the muon begins high above Earth and later reaches the detector. Relativity preserves the event structure. It changes the coordinates assigned to those events. Length contraction follows directly from the same transformation. Suppose a spacecraft has a certain length when measured at rest. This is its proper length. An observer watching the spacecraft move measures a shorter length along the direction of motion. The faster it moves, the greater the contraction. At low speeds, the difference is negligible. Near light speed, it can become large. Only the direction of motion contracts. A spacecraft moving horizontally does not become shorter vertically due to ordinary Lorentz contraction. This is another reason simple drawings of squeezed moving objects can be misleading. The contraction belongs specifically to the dimension parallel to relative velocity. There is also a subtle difference between measurement and appearance. A photograph of a relativistically moving object does not necessarily look like a simply shortened version of the object. Light from different parts takes different times to reach the camera. While the light travels, the object continues moving. These light travel time effects can make the object appear rotated or otherwise distorted. The measured Lorentz contraction is defined more carefully. The observer records the position of the front and rear at the same time in that observer's frame. Then the distance between those simultaneous positions is measured. The word simultaneous becomes essential, and simultaneity itself is relative. This is where the three main effects connect. To measure the length of a moving train, an observer must locate its front and rear simultaneously, but another observer moving relative to the first does not generally agree that those two measurements happen at the same time. So observers disagree about length partly because they disagree about simultaneity. Length contraction is therefore not an isolated physical squeezing. It emerges from how different observers divide spacetime into space and time. A useful thought experiment uses a long train. Imagine lightning striking both ends of the train. An observer standing at the midpoint of the railway receives light from both strikes simultaneously. Assume that observer has already corrected for equal distance to the two ends. The railway observer therefore concludes that the strikes occur at the same time. Now consider an observer sitting at the midpoint of the moving train. The train moves toward the location of one flash. It moves away from the other. Light from both strikes travels at the same speed c relative to the train observer, so the train observer receives one flash before the other. The train observer concludes that the events were not simultaneous. This difference is not caused by light moving faster toward one observer. Both observers measure the same light speed. It is the timing of the distant events that differs between frames. This is the relativity of simultaneity. It may be the most conceptually important result of special relativity. Time dilation often receives more attention, but simultaneity explains why reciprocal time dilation is possible. Observer A says B's clock runs slowly. Observer B says A's clock runs slowly. How can both statements remain consistent? Because comparing distant clocks requires a convention for what counts as happening at the same time. A and B disagree about distant simultaneity. Each builds a different set of simultaneous slices through spacetime. Their statements about the other clock refer to different pairs of events. There is no direct logical contradiction. The issue becomes clearer with synchronized clocks. Imagine a long row of clocks along a railway. The railway observer synchronizes them using light signals and the rule that light travels equally fast in both directions. Now a train passes. Observers on the train look at the railway clocks. According to the train frame, those clocks are not synchronized. Clocks farther ahead show a different time from clocks farther behind. The railway observer believes they are synchronized. The train observer does not. Now reverse the setup. The train contains a row of synchronized clocks. The railway observer says the train clocks are not synchronized. Each frame regards its own clocks as synchronized. Each sees the other's network as offset. This relativity of synchronization removes much of the mystery. A moving clock runs slowly, but distant clocks in the moving frame are also considered out of synchronization. Both effects are required by the Lorentz transformation. Ignoring the second while keeping the first produces paradoxes. The relativity of simultaneity also changes the meaning of the present. Consider two very distant stars. An observer on Earth may define certain events at those stars as happening now. An observer moving rapidly relative to Earth may define a different pair of distant events as simultaneous with the same Earth event. There is no unique universal present stretching across space. This does not create practical confusion in ordinary life. Human relative speeds are small. Distances within daily experience are modest. The differences are microscopic. But across astronomical distances and high relative velocities, the difference can become large. Space-time does not come naturally sliced into one universal stack of moments. Each inertial frame slices it differently. Minkowski diagrams make this easier to visualize. A space-time diagram usually places space horizontally and time vertically. An observer at rest remains at one spatial position. Its world line appears vertical. A moving observer follows a tilted line. Light follows diagonal lines. Because the speed of light is invariant, the light lines form the same causal boundary for every observer. But the moving observer's axes are tilted relative to the stationary observer's axes. The moving time axis leans. So does the moving space axis. A line representing simultaneous events for one observer does not represent simultaneous events for another. This geometric tilt contains time dilation, length contraction, and relativity of simultaneity together. Nothing separate needs to be added. The Lorentz transformation is essentially a rotation of space-time coordinates, not an ordinary Euclidean rotation. Space and time have a different geometric relationship, but the analogy is useful. Imagine two people drawing coordinates on the same sheet. One set is rotated. They disagree about the x and y components of a line, yet they agree on its geometric length. In relativity, observers disagree about spatial and temporal components, yet they agree on the space-time interval. The interval remains invariant. This invariant becomes the deeper quantity. Suppose two events are separated by some distance in space and some duration in time. Different observers assign different values to those separations. One may measure more spatial distance and less time, another less distance and more time. Yet a certain combination remains unchanged. That combination is the space-time interval. For events that a massive object can travel between, the interval relates directly to proper time. Every observer calculates the same proper time for the object following that world line. This is the geometric heart of the twin paradox. Two twins begin together. One remains near Earth. The other travels away at relativistic speed, then turns around and returns. When they meet again, the traveler has experienced less proper time. The phrase paradox suggests contradiction. There is none. The confusion usually comes from the symmetry of motion. During the outward journey, Earth says the traveler moves. The traveler can say Earth moves. Both see the other's clock as slow. During a constant velocity segment, the symmetry is real, but the complete journeys are not symmetric. The traveling twin changes velocity. The traveler switches inertial frames. The Earth twin follows a different space-time path. When both reunite, their clocks can be compared at one location. The result is objective. The traveler's clock shows less elapsed time. Acceleration explains which twin changes frames. But acceleration itself is not the main source of the aging difference. The deeper explanation is different world lines. Imagine modifying the journey so the turnaround acceleration happens very quickly or gradually. As long as the overall space-time path remains similar, the proper time difference remains. The acceleration determines how the traveler transitions between inertial segments. The accumulated aging difference comes from the complete path. This is often summarized using space-time geometry. In ordinary space, a straight path between 2 points is the shortest. In Minkowski spacetime, for time-like paths, the inertial straight world line between two fixed events gives the greatest proper time. A traveler who takes a bent world line through spacetime experiences less proper time. The geometry has a reversed flavor compared with ordinary distance. This can sound abstract. A simpler view uses actual numbers. Imagine a distant destination 8 light-years away in Earth's frame. A spacecraft travels at a speed close enough to light that Earth measures the trip as taking around 10 years each way. The exact numbers depend on velocity. Earth observers may age around 20 years during the round trip. The traveler's clocks may record much less. From the traveler's perspective, the clocks do not run slowly. Instead, the distance between Earth and the destination is length contracted. The destination is closer. The outward journey takes fewer traveler years. After turning around, the distance home is also contracted in the new inertial frame. The traveler and Earth agree when reunited. The path contains different proper times. The turnaround causes another important effect from the traveler's perspective. When the traveler changes frames, the definition of which distant Earth event is simultaneous with the turnaround changes. During the outbound leg, one set of Earth events is considered simultaneous. During the inbound leg, a later set is considered simultaneous. Earth's assigned present jumps forward in the traveler's coordinate description. This change resolves the naive claim that each twin should always see the other aging more slowly, and therefore both should end younger. The traveler's frame is not one inertial frame throughout the trip. The change in simultaneity during turnaround matters. This is one of the strongest examples of why relativity of simultaneity cannot be ignored. Time dilation alone gives only part of the story. Now consider a variation without sharp acceleration. Place 3 observers. Earth remains at rest. One spacecraft moves outward. Another moves inward. The outward traveler passes a distant meeting point and immediately transfers information to the inbound traveler. No individual traveler needs to reverse direction. The result still reproduces the same proper time difference when the inbound observer reaches Earth. This shows that acceleration is not fundamentally what makes moving clocks accumulate less time. The key is the path through spacetime. Acceleration simply provides a practical way for one traveler to follow both segments. The twin paradox becomes almost ordinary when viewed geometrically. Two paths connect the same departure and reunion events. The paths contain different proper time. Two clocks travel those paths. They record those different durations. Nothing mysterious needs to happen to the mechanisms. They simply measure the geometry. This suggests a useful phrase. A clock measures the length of its path through time. More precisely, it measures proper time along its space-time world line. Relativity turns clocks into geometric instruments. The same is true of rulers. A ruler measures spatial separation according to a chosen frame. Different frames divide space-time differently, so the spatial part can change. Time and space trade contributions while the deeper interval remains invariant. This also explains why no massive observer can have a rest frame moving at the speed of light. As velocity approaches c, the Lorentz factor diverges. The transformations required to create a photon rest frame become undefined. It is therefore incorrect to ask what time feels like from a photon's perspective. There is no valid inertial rest frame for light in special relativity. A photon has zero proper time along its null path. But this does not mean a photon experiences the universe instantaneously in an ordinary psychological sense. Experience requires a rest frame and clock. Light has neither. The proper statement is mathematical. The space-time interval along a light-like trajectory is zero. That is all. This is an example where ordinary language can create unnecessary confusion. Relativity does not say that photons see everything at once. It says no inertial coordinate system can move alongside a photon at c. Now consider the famous phrase, "Nothing can travel faster than light." This also requires precision. Special relativity says no ordinary object with Dungo rest mass can be accelerated from below c to above c through continuous physical acceleration, and no usable information or causal influence has been observed traveling faster than c in vacuum. Some situations can produce apparent faster-than-light motion without violating relativity. For example, a laser spot projected across a very distant surface can move faster than light if the laser is swept rapidly. No physical object moves along the surface from one illuminated point to the next. Each spot is created independently by different photons. No message travels between neighboring spots. Likewise, certain astronomical jets appear to move across the sky faster than light. This is called apparent superluminal motion. The effect comes from geometry. A jet moves close to light speed at a small angle toward Earth. Light emitted later has less distance to travel to the observer than light emitted earlier. The observed time interval becomes compressed. The apparent sideways motion can exceed c. The actual material remains below light speed. Another confusing phenomenon involves the phase velocity of waves. Certain wave patterns can have phase velocities above c. But those patterns do not necessarily carry information at that speed. The relevant speed for causality is associated with signal propagation. Relativity remains intact. Quantum entanglement creates another apparent challenge. Two entangled particles can display correlations over enormous distances. Measurements reveal connections stronger than ordinary classical local models allow. But entanglement does not permit controllable faster-than-light messaging. Each local measurement result is individually unpredictable. Only after comparing results through ordinary slower-than-light communication do the correlations become visible. So quantum mechanics is strange, but it does not provide a simple communication channel through the relativistic speed limit. This relationship between relativity and quantum theory is important. Both are fundamental. A complete theory must respect both. Quantum field theory successfully combines special relativity with quantum mechanics. Particles become excitations of fields. Antiparticles appear naturally. Energy and momentum obey relativistic rules. The speed c remains built into causal structure. Relativity is therefore not replaced by quantum mechanics. They coexist. Special relativity becomes part of the foundation of modern quantum theory. One result of combining relativity and quantum mechanics is antimatter. The Dirac equation is a relativistic quantum equation for electrons. Its mathematical structure leads to negative energy solutions. These eventually become understood as corresponding to positrons. Positrons are the antimatter partners of electrons. This was a remarkable prediction. Relativity helped reveal particles that had not yet been observed. Antimatter is not matter traveling backward through time in any simple literal sense. Certain mathematical interpretations allow antiparticles to be represented in diagrams as particles moving backward in time. But physically, positrons travel forward in time like ordinary particles. They carry positive energy. They can be detected. They annihilate with electrons. The backward time description is a computational interpretation in quantum field theory, not a statement that antimatter can visit the past. This distinction is useful because relativity and time travel are often mixed together too quickly. Special relativity certainly allows different observers to experience different elapsed times. A traveler can move into Earth's future by traveling near light speed and returning. This is real one-way time travel into the future. The traveler simply experiences less time than Earth. But special relativity does not provide an ordinary method for returning into the past. Backward time travel creates causality problems. If a signal could travel faster than light in one inertial frame, Lorentz transformations can produce another frame in which the signal travels backward in time. This is why superluminal communication is so deeply connected to causal paradoxes. It is not merely that t is a fast number. It is woven into the structure of cause and effect. The light cone divides spacetime. Inside the future cone are possible future influences. Inside the past cone are possible causes. Outside are space-like separated events. A faster-than-light signal would cross outside the light cone. Then different frames could disagree about temporal order. With suitable arrangements, a return message could arrive before the original message was sent. Relativity would permit a causal loop. This is one reason the speed limit protects chronology. Now return to ordinary sublight motion. Another relativistic effect is the Doppler shift. A familiar Doppler effect occurs with sound. A passing ambulance has a higher pitch while approaching, a lower pitch while receding. The source and observer move relative to the air carrying the sound. Light also shows a Doppler effect, but because there is no required ether medium, and because E is invariant, the relativistic Doppler formula differs from the ordinary sound formula. A source moving toward an observer is blue shifted. Its observed frequency increases. A source moving away is red shifted. Its frequency decreases. This effect is extremely important in astronomy. Spectral lines from stars and galaxies can reveal motion. A moving source shifts known atomic wavelengths. Measure the shift. Infer radial velocity. At low speeds, classical approximations work. At high speeds, the full relativistic relationship is required. Relativistic Doppler shift combines time dilation with changing separation. Suppose a spacecraft moves away while emitting pulses at equal intervals in its rest frame. The observer receives the pulses farther apart for two reasons. The source's clock is time dilated, and each new pulse begins from a slightly greater distance. The combination produces the relativistic redshift. When the source approaches, changing distance works in the opposite direction. The frequency increases. This effect can be understood symmetrically. Each inertial observer sees the other's clock as slow. Each also sees received signal spacing altered according to whether they approach or recede. The observed Doppler shift does not directly equal the bare time dilation factor. Geometry of propagation matters. This becomes important in the twin paradox. During the outbound journey, Earth sees the traveler's signals strongly redshifted. The traveler also sees Earth's signals redshifted. During the inbound journey, both see each other blue shifted. The asymmetry in how long each phase lasts leads to the final age difference. Signal exchange gives a completely operational way to analyze the problem. No distance simultaneity convention is required to compare what each actually receives. Relativity can always be described in terms of clocks and exchanged light. This is one reason Einstein's reasoning was so powerful. Abstract time becomes a question of procedures. How are clocks synchronized? How are distances measured? When do signals arrive? What does an observer actually record? This operational approach removes vague assumptions. A clock reading is an event. A light pulse connects events. A ruler measurement requires simultaneous endpoint positions. Every concept is tied to a possible observation. Another famous thought experiment involves a barn and a pole. A pole is longer than a barn. When both are at rest, the pole then moves through the barn at relativistic speed. From the barn frame, the pole is length contracted. It can briefly fit completely inside. Both doors could, in principle, close simultaneously in the barn frame. But from the pole's frame, the barn is moving. The barn is length contracted. It becomes even shorter. How can the pole fit? The solution is relativity of simultaneity. In the pole frame, the two barn doors do not close at the same time. The front door closes and opens at a different moment from the rear door. There is never a moment in the pole frame when the entire long pole sits inside a simultaneously closed short barn. In the barn frame, there is such a moment. Different frames disagree about simultaneity. They do not disagree about actual local events. Each door closes when the pole reaches certain positions. Every observer agrees on the intersection events between pole and door. The apparent contradiction disappears. This example may sound artificial, but it highlights a general rule. Many relativity paradoxes are really simultaneity paradoxes. Another version is the latter paradox. The story changes. The physics does not. Whenever two distant things must happen at the same time, the phrase same time must be tied to a frame. Without specifying the frame, the statement is incomplete. This is one of the best habits for understanding relativity. Whenever a claim involves time, ask, time according to which observer? Whenever a claim involves length, ask, measured in which frame? Whenever a claim says two events are simultaneous, ask, simultaneous, in which frame? These questions often dissolve confusion immediately. The need to specify an observer does not make physics subjective. Measurements transform according to exact equations. Different observers are not free to invent arbitrary answers. If one observer knows an event's coordinates and the relative velocity, the other observer's coordinates can be calculated. The Lorentz transformation tells them exactly how. Relativity is therefore highly constrained. It replaces absolute measurements with invariant relationships. This makes the theory more geometric, not less precise. There is also a beautiful symmetry between space and time in the Lorentz transformation. A change in spatial coordinate depends partly on time. A change in time coordinate depends partly on space. This mixing is why simultaneity becomes relative. Under Galilean transformations, time remains unchanged. Every observer shares the same t, only position changes. Under Lorentz transformations, both change. Space and time become inseparable. Minkowski's language makes this explicit. There is no longer space on one side and time on another. There is space-time. Still, time is not simply another identical spatial dimension. The space-time metric treats it differently. The signs in the interval differ. This mathematical difference creates the causal structure of light cones. A person can choose to move left or right through space. A massive object cannot freely choose to move backward through its proper time. Time has a different geometric character, so saying time is the fourth dimension is useful. But it should not imply perfect interchangeability with spatial dimensions. Space-time unifies them while preserving an important distinction. Another geometric idea is rapidity. Ordinary velocities do not add linearly near light speed. Suppose one spacecraft moves at 80% of c relative to Earth. Another moves at 80% of c relative to the first in the same direction. Simple addition would give 1.6 c. That cannot be correct. Relativistic velocity addition produces a result below c. No sequence of ordinary sublight boosts exceeds the invariant speed. The closer velocities get to c, the more strongly the addition rule differs from ordinary arithmetic. Rapidity provides a mathematical variable that does add simply. Instead of adding velocities directly, boosts can be described by adding rapidities. The resulting physical velocity remains below c. This is another sign that ordinary velocity is not the most natural geometric parameter in relativity. The mathematics becomes simpler when expressed in terms suited to spacetime. At everyday speeds, relativistic velocity addition becomes nearly ordinary addition. Again, Newtonian intuition emerges as the low-speed approximation. Suppose one spacecraft moves at 10 kilometers per hour relative to another. The correction from relativity is impossibly small for casual observation. 10 plus 10 is effectively 20. Only at enormous speeds does the difference become obvious. Nature has not changed rules between cars and spacecraft. The same relativistic rule always applies. The classical rule merely approximates it extremely well when velocity divided by c is tiny. This is an important scientific lesson. An approximation can appear absolute within a limited domain. Human intuition develops around that domain. Then a broader theory reveals the approximation. Relativity feels strange, partly because human bodies never naturally encounter its strong regime. There is another effect called relativistic aberration. As an observer moves rapidly, the apparent directions of incoming light shift. Stars appear concentrated toward the direction of motion. At speeds close to c, much of the sky seems compressed into a forward cone. This resembles the way rain appears to come more from the front when a person runs through it, but relativity makes the effect more extreme. Combined with Doppler shifting, the forward sky can become blue shifted, the backward sky red shifted. Brightness can also change through relativistic beaming. These effects matter in astronomy. Jets moving near light speed can appear strongly brighter when pointed partly toward Earth. Emission is concentrated in the forward direction of motion. This is why orientation can dramatically affect the appearance of active galaxies. A jet aimed toward Earth may create an object classified differently from the same physical system viewed sideways. Relativity changes observed brightness, as well as clocks and rulers. This is not because the source intrinsically produces more power in the observer's direction in its own frame. Motion changes how radiation is distributed in the observer's frame. Photon energies shift, arrival rates change, angles compress. The combination produces beaming. Relativity therefore influences almost every astronomical measurement involving fast-moving material. Black hole jets, neutron star winds, gamma-ray bursts, cosmic rays, high-energy particles. The universe contains many natural relativistic laboratories. Earth-based accelerators, add controlled ones. Another subtle idea concerns acceleration. Special relativity is often introduced as the theory of constant speed motion. But special relativity can still describe accelerating objects as long as gravity and spacetime curvature can be neglected. An accelerating observer simply changes inertial frames continuously. The laws become more complicated in non-inertial coordinates. But special relativity remains applicable in flat spacetime. General relativity becomes necessary when gravity is treated as spacetime curvature. This distinction matters because the phrase special relativity only works without acceleration is too simplistic. Accelerating rockets can be analyzed within special relativity. What special relativity assumes fundamentally is flat spacetime. Einstein's path toward general relativity begins by considering acceleration more deeply. Suppose a person stands inside a sealed elevator. The elevator is far from stars and planets. A rocket accelerates the elevator upward. The person feels pressed against the floor. Release a small object. The floor accelerates upward toward it. From inside, the object appears to fall. Now imagine an elevator resting on Earth's surface. Release the same object. It falls. Locally, the two situations can look remarkably similar. Acceleration and gravity seem connected. This becomes the equivalence principle. But before moving to gravity, special relativity contains one more useful lesson about energy. At low speeds, kinetic energy is approximately 1/2 mv squared. This familiar expression comes from Newtonian mechanics. At relativistic speeds, the exact energy relationship differs. As velocity approaches c, kinetic energy rises without bound. The speed approaches c asymptotically. Adding more energy keeps increasing momentum, but the speed changes by smaller and smaller amounts. This is observed in particle accelerators. A proton can be given enormous amounts of additional energy, while its speed changes only slightly once it is already extremely close to c. The extra energy does not disappear. It appears in the particle's total energy and momentum. This is why modern accelerators are often described by particle energy rather than speed. Two very different beam energies may correspond to speeds that both round to nearly 100% of c. The energy difference remains physically enormous. When high-energy particles collide, their kinetic energy can create new particles. This is mass-energy equivalence in action. Energy can become rest mass. A collision concentrates enough energy. New massive particles appear. The reverse also occurs. Mass can become other forms of energy. Particle-antiparticle annihilation converts rest energy into radiation. Nuclear reactions convert small differences in mass into released energy. Stars shine through such processes. The equation E equals mc squared gives the rest energy associated with mass. Because c squared is enormous, even a small mass corresponds to an enormous amount of energy. 1 gram of matter has a rest energy far beyond ordinary chemical energies. This does not mean every gram can easily be converted entirely into usable energy. Most processes convert only a tiny fraction. The equation describes equivalence, not an engineering recipe. Mass-energy equivalence also changes how composite systems are understood. A box containing energetic radiation has more mass than the same box after the radiation leaves. A bound atomic nucleus can have less mass than the sum of its separated components because energy is released when the nucleus forms. This difference is binding energy. The same principle appears in stars. Nuclear fusion converts some mass energy into radiation. The sun gradually loses mass by radiating energy. Relativity, therefore, connects directly to stellar physics. Special relativity also clarifies momentum conservation. In Newtonian mechanics, momentum equals mass times velocity. At high speeds, relativistic momentum includes the Lorentz factor. This ensures momentum remains conserved in every inertial frame. Energy and momentum are unified into a four-dimensional object called four-momentum. Just as space and time combine into spacetime, energy and momentum combine naturally in relativistic physics. The invariant length of four-momentum relates to rest mass. This parallel is elegant. Space pairs with time, momentum pairs with energy. The transformations mix them, yet invariants remain. Modern physics becomes filled with four vectors: position 4 vector, velocity 4 vector, momentum 4 vector, electromagnetic 4 potential. The notation reflects the underlying symmetry of spacetime. This mathematical structure is one reason special relativity reaches far beyond the original problem of moving clocks. It reorganizes physics. Electromagnetism becomes naturally relativistic. Electric and magnetic fields themselves turn out to be different aspects of one electromagnetic field. An observer may measure mostly an electric field. Another observer moving relative to the first can measure a mixture of electric and magnetic fields. Magnetism can partly be understood as a relativistic aspect of electricity. This is a profound connection. Consider electric charges in a wire. In one frame, charge densities and currents have certain values. In another moving frame, length contraction changes those densities. The balance between positive and negative charge can look different. What appears as a magnetic force in one frame can be related to electric forces in another. Electricity and magnetism are not completely separate phenomena. Relativity helps reveal their unity. Maxwell's equations already hinted at this. Their structure naturally contains the invariant speed c. Einstein's special relativity makes that symmetry central. The theory does not merely adjust mechanics to fit electromagnetism. It shows that space-time itself has the symmetry Maxwell's equations require. This is one reason relativity was such a deep conceptual advance. The problem was not that light behaved strangely inside ordinary space and time. The deeper issue was that ordinary assumptions about space and time were incomplete. Once space-time is understood relativistically, light behaves naturally. The equations stop fighting one another. This is often how fundamental physics progresses. A strange observation may not require adding another mechanism. It may require changing the framework in which the observation is interpreted. The invariant speed of light led to a new framework for time. Later, gravity leads Einstein to change the framework again. Before that step, it is useful to gather the main ideas of special relativity slowly. There is no preferred inertial frame. Every inertial observer can regard themselves as at rest. The laws of physics have the same form in each inertial frame. Light in vacuum has the same speed c for each. To make this possible, space and time cannot remain absolute. Moving clocks are measured as running slowly. Moving lengths are measured as contracted along the direction of motion. Distance simultaneity depends on the observer's motion. Observers disagree about coordinates. They agree about space-time intervals. A clock measures proper time along its world line. Different world lines between the same events can contain different amounts of proper time. This resolves the twin paradox. The traveling twin ages less because the twins follow different paths through space-time. The symmetry of constant relative motion is broken by the traveler's change of frame. No massive object can be accelerated to c with finite energy. Relativistic velocity addition keeps sublight speeds below c. Apparent superluminal effects can occur without carrying matter or information faster than light. Light cones organize causal structure. Time-like separated events have an invariant order. Space-like separated events can have frame-dependent order. Because neither can causally influence the other within the relevant interval, the present is therefore not universal. Space and time combine into space-time. Mass and energy are related. Energy and momentum combine into momentum. Electricity and magnetism become aspects of one electromagnetic field. These are not isolated curiosities. They are parts of one coherent geometry. And yet special relativity leaves one enormous question unanswered. Gravity. Newton's gravity appears to act instantly across distance. Special relativity says causal influences cannot propagate faster than light. The two pictures do not fit comfortably. There is also another problem. Gravity and acceleration seem strangely similar. A person standing on Earth feels weight. A person inside an accelerating rocket can feel nearly the same thing. An observer falling freely feels weightless even though gravity is present. Einstein begins to suspect that gravity may not be an ordinary force at all. Perhaps objects in freefall are doing something simpler. Perhaps they are following the natural straightest paths available to them. And perhaps the reason those paths appear curved is that space-time itself is curved. This idea becomes general relativity. The transition is profound. Special relativity changes measurements within flat space-time. General relativity allows space-time itself to change shape. Mass, energy, pressure, and momentum affect that geometry. The geometry then guides matter and light. Gravity becomes space-time curvature. In the next part, the equivalence principle will open that door, showing why free fall feels weightless, why standing still on Earth is actually an accelerated state, how Einstein connects gravity with geometry, and why curved spacetime replaces the old picture of an invisible gravitational force reaching across space. General relativity begins with a very ordinary sensation: weight. A person standing on Earth feels pressure beneath the feet. A chair pushes upward. The floor resists downward motion. This sensation feels so familiar that it seems natural to call it gravity. But Einstein notices something subtle. A freely falling person does not feel this same force. Imagine an elevator whose cable has been released. Inside, the elevator and everything within it fall together. A person releases a small object. The object does not immediately drop toward the elevator floor. Instead, it floats nearby. The person, the object, and the elevator all accelerate downward together. Locally, gravity seems to disappear. This is the beginning of the equivalence principle. Einstein realizes that free fall has a special status. A freely falling observer behaves locally as though gravity were absent. This is almost the reverse of ordinary intuition. Standing still on Earth feels natural. Falling feels accelerated. General relativity changes that perspective. The freely falling object follows the natural path. The person standing on the ground is prevented from following that path. The ground continuously pushes upward. In this sense, standing still on Earth involves acceleration. Free fall does not. An accelerometer makes the distinction clear. Place an accelerometer inside a spacecraft drifting far from planets. It reads approximately 0. Fire the engines. The spacecraft accelerates. The instrument records that acceleration. Now place the same instrument in free fall near Earth. It again reads approximately 0. Place it on the ground. It records an upward proper acceleration. The ground is preventing the instrument from following its natural free fall trajectory. This is one of general relativity's most surprising reversals. Gravity is not treated as an ordinary force pulling freely falling objects downward. Instead, free objects follow the natural geometry of spacetime. The ground interferes. A person standing on Earth feels weight because the ground keeps the person away from the natural freefall path. The sensation, usually called gravity, is largely the sensation of being supported. This can be seen in orbit. Astronauts aboard an orbiting spacecraft often appear weightless, yet gravity has not vanished. At the altitude of a low Earth orbit, Earth's gravitational field remains strong. The spacecraft falls toward Earth continuously. The astronauts fall with it. Their sideways motion is fast enough that the curved Earth keeps dropping away beneath them. They remain in perpetual free fall. Orbit is not an escape from gravity. Orbit is falling without reaching the ground. This becomes much easier to understand geometrically. Imagine throwing a ball horizontally. It moves forward while gravity bends its path downward. Throw it faster. It travels farther before reaching the ground. Throw it fast enough, ignoring air resistance and obstacles. The surface of Earth curves away at the same rate that the ball falls. The ball continues around the planet. This is an orbit. Newton understands this using gravitational force. Einstein describes the same motion more deeply. The orbiting body follows a geodesic through curved spacetime. A geodesic is the closest generalization of a straight path. On a flat sheet of paper, the shortest route between nearby points is a straight line. On a curved surface, the corresponding path can look curved when viewed from outside. A great circle route on Earth is an example. Airplanes traveling between distant cities often follow great circle paths. On a flat map, these routes can appear bent. On the spherical Earth, they are the natural straightest paths. General relativity extends this idea into four-dimensional spacetime. Planets, moons, falling stones, and freely moving spacecraft follow geodesics. The black hole does not contain a solid surface vibrating like metal. Its spacetime geometry oscillates. Those oscillations produce gravitational waves. The frequencies are called quasi-normal modes. They depend primarily on the final black hole's mass and spin. This creates an extraordinary possibility. Measure the ring-down frequencies, infer the properties of the black hole, then compare them with the predictions of general relativity. A stationary astrophysical black hole is expected to settle toward the Kerr geometry if charge is negligible. The Kerr solution is determined mainly by mass and angular momentum, so the ring-down has relatively little freedom. If several measured modes fail to match one Kerr black hole, that could signal something unexpected. Perhaps the object differs from the general relativistic prediction. Perhaps the data contain noise. Perhaps the model is incomplete. Future high-precision observations may allow a form of black hole spectroscopy, like identifying an instrument by its characteristic tones. But instead of sound, the tones are frequencies of spacetime. The complete compact binary signal is therefore often divided into three broad stages: inspiral, merger, ringdown. The boundaries are not perfectly sharp. They are useful conceptual categories. The inspiral reveals the long orbital dance. The merger reveals the strongest dynamical geometry. The ringdown reveals the final black hole settling. Each phase tests relativity differently. Long before direct detection, astronomers find indirect evidence for gravitational waves. A famous example comes from a binary pulsar discovered in the night. The system contains a neutron star observed as a pulsar orbiting another compact object. A pulsar emits radio pulses with remarkable regularity. This makes its orbit measurable with great precision. General relativity predicts that the binary should lose energy through gravitational radiation. The orbit should slowly shrink. The orbital period should change. Years of timing observations reveal exactly such a change. The amount closely matches the relativistic prediction after known effects are included. The system therefore behaves as though energy is leaving in gravitational waves. The waves themselves are not directly detected there, but the orbital decay provides powerful indirect evidence. It is similar to watching a boat lose energy while ripples spread beyond the visible horizon. Even before the ripples are seen directly, the boat's motion reveals energy leaving. Direct detection requires something far more sensitive. Gravitational waves arriving at Earth are extraordinarily weak. A passing wave changes the distance between freely moving objects. One direction stretches slightly, a perpendicular direction compresses slightly. Then the pattern reverses. The effect is described using a quantity called strain. Strain is the fractional change in length. If a distance L changes by a tiny amount, the strain is the change divided by L. Astrophysical gravitational wave strains measured at Earth can be unbelievably small. This is why detectors need long arms and extraordinary precision. The Laser Interferometer Gravitational Wave Observatory, usually called LIGO, uses laser interferometry. Each detector has two long arms arranged approximately at right angles. A laser beam is split. One part travels down one arm, the other travels down the second. Mirrors reflect the beams back. The light is recombined. If the two paths remain exactly related, the interference pattern behaves in a predictable way. A gravitational wave slightly changes the relative lengths of the arms. One can stretch while the other contracts. Then the pattern alternates. This changes the interference of the returning laser light. From that tiny change, the wave can be inferred. The arms are kilometers long, but the changes being measured are far smaller than anything visible. The challenge is not merely building a precise ruler. The detector must distinguish gravitational waves from countless sources of noise: ground vibration, seismic motion, thermal motion, wind, electrical noise, mechanical disturbances, quantum fluctuations in the laser measurement. Even distant human activity can matter. The mirrors are suspended carefully. Vacuum systems reduce disturbances. Multiple layers of isolation separate the optics from ground motion. The entire instrument behaves like one enormous precision experiment. Still, one detector alone is not enough for many purposes. A disturbance could be local, so gravitational wave astronomy uses networks. LIGO operates multiple detectors. Virgo operates in Europe. COGRA operates underground in Japan. Additional detectors in future facilities expand the network. If a true gravitational wave passes Earth, separated detectors should observe related signals with timing differences determined by the wave's direction. A local disturbance at one site will usually not reproduce the same pattern elsewhere. Multiple detectors therefore improve confidence. They also help locate the source on the sky. A wave reaches one detector slightly before another. The time difference constrains its direction. Add more detectors. The sky region narrows. This resembles triangulation. The waveform itself provides further information. General relativity predicts the shape of signals produced by compact binaries. The masses influence the frequency evolution. Spin changes the phase. Orbital orientation affects the amplitude and polarization. Distance influences signal strength. By comparing measured data with theoretical waveforms, astronomers can estimate the source properties. This method is called matched filtering. For many searches, a large library of predicted waveforms is compared with detector data. The goal is to find the pattern that best matches a potential signal. This works because a compact binary waveform is highly structured. It is not random noise. The phase evolves according to gravity. A signal can therefore be hidden beneath noise at individual moments, while still becoming detectable through its coherent pattern. It is similar to recognizing a faint repeating melody inside a noisy room. The individual notes may be difficult to hear. The full pattern reveals the song. In 2015, LIGO observes a signal from a merging pair of black holes. The event becomes the first direct detection of gravitational waves. It also becomes the first direct observation of a binary black hole merger through gravitational radiation. The signal travels across the universe for an immense distance, then passes Earth. The arms of the detectors change by a tiny fraction. From this almost imperceptible motion, scientists reconstruct an event involving black holes with masses many times that of the Sun. This is one of the most striking demonstrations of general relativity. Einstein's equations predict that accelerating compact masses disturb spacetime. A century later, instruments measure those disturbances directly. The event also confirms that stellar mass black holes can exist in close binary systems and merge. Before gravitational wave astronomy, black holes were commonly studied through electromagnetic effects, gas heating and accretion disks, X-rays, stellar motion, radio jets. But two isolated black holes can be almost completely dark. They may emit little ordinary light. Gravitational waves allow such systems to become visible in a new sense. The detector does not need the black holes to glow. It listens to the geometry. This creates an entirely new form of astronomy. Traditional astronomy observed electromagnetic radiation, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Different wavelengths reveal different processes. Gravitational wave astronomy adds a new messenger. Instead of photons, the messenger is changing space-time curvature. Neutrino astronomy adds another messenger. Cosmic rays add another. When several kinds of signals are observed from one event, the approach is called multi-messenger astronomy. A particularly important example occurs when two neutron stars merge. Unlike black holes, neutron stars contain matter. Their collision can produce gravitational waves and electromagnetic radiation. The gravitational signal reveals the orbital motion. The light reveals hot matter, nucleosynthesis, and ejecta. Together they tell a richer story than either messenger alone. A neutron star merger detected through gravitational waves can also produce a short gamma-ray burst. Observing both provides a powerful test. The arrival times show that gravitational waves and light travel at extremely similar speeds across cosmic distance. This strongly constrains theories in which gravity propagates at a noticeably different speed. General relativity predicts propagation at c. Observation agrees to remarkable precision. The same event can help explain where some heavy elements form. Neutron-rich material thrown from the merger undergoes rapid nuclear reactions. Elements heavier than iron can be created. Gold, platinum, and other heavy nuclei may be produced in substantial quantities in such events. Relativity therefore connects to chemistry in an unexpected way. The geometry of merging neutron stars can help create some of the atoms later incorporated into planets. General relativity also influences the structure of neutron stars themselves. A neutron star contains roughly stellar-scale mass compressed into a sphere only tens of kilometers across. Its gravity is strong enough that Newtonian hydrostatic equilibrium is insufficient. Pressure supports the star, but pressure itself contributes to gravity in relativity. The internal structure must be described using relativistic equations. One important equation is the Tolman-Oppenheimer-Volkoff equation. A locally inertial frame itself is dragged, so an observer can distinguish rotation relative to local spacetime from rotation relative to distant infinity. These distinctions become important in precision calculations. They also show how much deeper the theory has moved from everyday notions of spinning objects. The rotation of a black hole is not represented by seeing a material surface turn. There is no ordinary surface. Spin is inferred from geometry. The exterior spacetime carries angular momentum. Matter orbits differently because of it. Light bends differently. Gyroscopes precess. The ergosphere appears. Gravitational waves encode spin. This means a black hole can rotate in a measurable sense even though there is no solid sphere to watch. The rotation belongs to the gravitational field and horizon structure. This is one reason black holes are such clean laboratories for relativity. A star has a surface, magnetic fields, chemical layers, differential rotation, convection, complex plasma. A settled black hole is simpler. According to the classical no-hair idea, an isolated stationary black hole is characterized by only a few global properties: mass, angular momentum, and electric charge. Astrophysical charge should generally be tiny, because surrounding plasma neutralizes large charge quickly, so mass and spin dominate. This simplicity allows precise tests. Measure the mass, measure the spin. General relativity predicts the exterior geometry. Observe orbits, accretion, lensing, and gravitational waves. Compare them with Kerr. Any consistent discrepancy could reveal new physics. This idea is sometimes called testing the Kerr hypothesis. One method uses stellar motion around supermassive black holes. Another uses accretion spectra. Another uses horizon-scale imaging. Future gravitational wave observations may provide especially clean tests. A small compact object spiraling into a much larger black hole could trace the geometry over many thousands of orbits. Such a system is called an extreme mass ratio in spiral. The small object acts almost like a probe. Each orbit samples the spacetime. The gravitational waves carry a detailed record. A future space-based detector could potentially reconstruct the central object's multipole structure. In general relativity, a Kerr black hole's higher multipole moments are determined by mass and spin. If observations reveal an independent extra structure, something would be different from Kerr. This is sometimes described as mapping the spacetime. No photograph of the horizon is required. The orbit itself becomes the map. This is a beautiful feature of relativity. Geometry can be measured by motion. Drop a test object, watch its path, send light, measure its delay, orbit a clock, measure its precession, listen to gravitational waves. The geometry reveals itself through relationships. The universe does not need to display a visible grid. Motion traces the invisible structure. The same principle underlies ordinary gravity near Earth. A falling apple traces a geodesic. Mercury traces the sun's curvature. A binary pulsar traces relativistic dynamics. A black hole in spiral traces Kerr geometry. Different scales, same idea. Rotation adds another layer to those paths. A prograde orbit feels one geometry. A retrograde orbit another. A tilted orbit precesses. The difference carries information about angular momentum. This is why spin is not merely an optional decoration. It is part of the spacetime. The most familiar spacetime diagram often suppresses rotation. It shows radial distance and time. That works for spherical symmetry. Kerr spacetime requires an angular structure. The geometry has an axis. The direction of spin matters. Perfect spherical symmetry is lost. Axisymmetry remains. Rotating the entire system around the spin axis does not change the geometry. But flipping the direction of motion can. This is how spacetime records handedness. A non-rotating Schwarzschild black hole does not prefer clockwise or counterclockwise. A Kerr black hole does. The preference is physical. Frame dragging distinguishes them. This can even influence the energy of orbits. Matter moving with spin can approach closer before becoming unstable. That increases the potential radiative efficiency of accretion. A non-rotating black hole can convert a certain fraction of an infalling object's rest mass energy into radiation through an ideal thin disk before the matter plunges. A rapidly rotating black hole with a prograde disk can, in principle, convert a substantially larger fraction. This helps explain why black hole accretion can be so luminous. Nuclear fusion converts only a small fraction of rest mass into radiation. Relativistic accretion can convert a larger fraction. A black hole can therefore power enormous luminosity without consuming a correspondingly enormous amount of matter every moment. The energy comes from gravitational binding. Matter falls deeper into the potential. It releases energy. Rotation can allow the disk to reach deeper still. The result can outshine entire galaxies. Quasars demonstrate this on cosmic scales. A quasar is powered by an actively accreting supermassive black hole. The black hole itself remains dark. The surrounding accretion flow produces tremendous radiation. Some quasars are visible across billions of light years. Their brightness once made their energy source puzzling. Relativistic accretion provides the answer. A relatively compact region near a black hole converts mass energy efficiently into radiation. The galaxy becomes a lighthouse. This also affects galaxy evolution. Radiation, winds, and jets from active black holes can heat or remove gas. The gas might otherwise form stars, so a small central region can influence a much larger galaxy. This process is called feedback. The detailed relationship between supermassive black holes and galaxies remains an active area of research, but observations show correlations between black hole mass and properties of galactic bulges. The histories appear connected. General relativity describes the central engine. Astrophysics connects that engine to the galaxy. Rotation often plays an important part through disk efficiency and jets. Thus, frame dragging reaches far beyond a local curiosity. It can influence how matter approaches a black hole, how energy is released, how jets form, and perhaps how galaxies evolve. An effect almost invisible around Earth becomes cosmically significant around black holes. This is a recurring lesson in relativity. Weak effects become strong when conditions become extreme. Time dilation on Earth is tiny. Near a horizon, it becomes enormous. Frame dragging on Earth is tiny. Near a Kerr black hole, it controls motion. Gravitational waves from ordinary moving objects are negligible. Black hole mergers make them detectable across the universe. The equations do not change, only the regime does. This continuity is reassuring. Relativity is not a collection of strange exceptions. It is one theory applied at different strengths. A bicycle technically follows relativistic mechanics. A laboratory clock experiences gravitational time dilation. Earth drags spacetime. The effects are simply small. Black holes magnify them. The extreme universe acts like a natural laboratory, where subtle equations become visible. Rotation also provides a useful bridge toward thermodynamics and quantum physics. A Kerr black hole has a horizon area, a surface gravity, an angular velocity, and a mass. These quantities satisfy relationships resembling the laws of thermodynamics. Energy added to the black hole changes its mass. Angular momentum added changes its spin. The horizon area responds. Classically, that area tends not to decrease. This resembles entropy. At first, the resemblance seems formal, then a problem appears. Suppose a box full of entropy falls into a black hole. From the outside, the box disappears behind the horizon. If the black hole has no entropy, the observable universe appears to have lost entropy. That would conflict with the second law of thermodynamics. Jacob Bekenstein proposes that black holes themselves must carry entropy, and that this entropy should be proportional to horizon area. The idea is bold. A horizon is geometry. Why should geometry have entropy? Then Stephen Hawking studies quantum fields around black holes. His calculation reveals that black holes emit thermal radiation. They possess temperature. The analogy becomes physical. A black hole is a thermodynamic object. This will lead to one of the deepest intersections in physics: general relativity, quantum theory, thermodynamics, and information. Rotation makes the story even richer because the black hole can exchange angular momentum as well as energy. A rotating black hole can lose spin. Its thermodynamic description includes rotational work. The same Kerr geometry that drags inertial frames also enters the quantum description. Relativity therefore points beyond itself. Einstein's classical theory predicts objects whose full understanding requires quantum mechanics. This is especially striking because general relativity and quantum theory were developed from very different ideas. Relativity describes smooth geometry. Quantum theory describes probabilities and discrete excitations. Each works extraordinarily well. Black holes force them into the same problem. The horizon belongs to gravity. Hawking radiation belongs to quantum fields. Entropy belongs to thermodynamics. Information belongs to quantum theory. All meet at one boundary. This is why black hole physics has become such an important guide toward quantum gravity. But before that quantum step, the classical picture can be gathered calmly. A rotating mass changes spacetime differently from a stationary one. Earth produces tiny frame dragging. A rapidly rotating compact object produces much more. The Kerr solution describes an ideal rotating black hole. Its exterior geometry depends mainly on mass and spin. An ergosphere appears outside the event horizon. Inside the ergosphere, complete stationary motion relative to infinity is impossible. Everything must share some of the rotation. Rotational energy can be extracted in principle. Magnetic fields can help transfer that energy outward. Stable orbits depend on whether motion follows or opposes the spin. Accretion efficiency depends on spin. Light paths depend on spin. Gravitational waves carry information about spin. A merged black hole settles into a Kerr state. The geometry itself records angular momentum, and this entire structure arises from one simple extension. Matter does not merely curve spacetime. Moving and rotating matter shape how that curvature is arranged. Spacetime can bend, it can wave, and it can twist. The next part will follow relativity into its connection with the universe as a whole, exploring how Einstein's equations describe an expanding cosmos, why the Big Bang is not an explosion into empty space, how cosmic redshift differs from ordinary Doppler shift, why distant galaxies can recede faster than light without violating special relativity, and how gravity shapes the history and geometry of the universe itself. General relativity does not only describe planets, stars, and black holes, it also describes the universe itself. This is one of the most remarkable consequences of Einstein's theory. Once space-time becomes dynamic, there is no reason the geometry of the entire cosmos must remain fixed. Space can expand, it can contract, its curvature can evolve. The universe becomes something that changes with time. This possibility appears directly in Einstein's field equations. When Einstein first applies his theory to the cosmos, the accepted picture is very different from the modern one. The universe is commonly imagined as eternal, static, and broadly unchanging on the largest scales. Einstein initially tries to construct a static cosmological model, but gravity creates a problem. Matter attracts matter. A universe filled with ordinary matter tends not to remain perfectly static. So Einstein introduces an additional term into his equations. This term becomes known as the cosmological constant. It can act in a way that counterbalances ordinary gravitational attraction in certain models. The goal is to preserve a static universe. But static cosmic solutions turn out to be unstable, and observations soon change the entire picture. Astronomers discover that distant galaxies are generally redshifted. The farther away they are, the greater the redshift tends to be. This becomes associated with the work of several scientists. Georges Lemaitre develops expanding universe solutions from general relativity and connects them with observational data. Edwin Hubble later helps establish the relationship observationally through galaxy distance measurements. The basic pattern becomes known as the Hubble-Lemaitre law. Distant galaxies recede from one another on large scales. The universe is expanding. This does not mean galaxies are simply flying outward through a pre-existing empty space from one central explosion. The expansion is more subtle. The distances between sufficiently separated, unbound regions grow because the cosmic geometry itself evolves. Space expands. This phrase can also be misunderstood. Space is not necessarily a substance being stretched like rubber. The statement means that the metric describing large-scale spatial distances changes with cosmic time. Two galaxies following the general cosmic expansion can remain approximately at rest in local co-moving coordinates, yet the proper distance between them increases. This is one of the places where general relativity differs sharply from ordinary motion through space. A useful analogy is a grid drawn on an expanding surface. Imagine many dots placed on the surface of a balloon. As the balloon inflates, every dot becomes farther from distant dots. No dot on the surface needs to be the center of expansion. Each observer sees many others receding. The analogy helps with one important point. Cosmic expansion does not need a center within the space being described, but the balloon analogy also has limitations. The two-dimensional balloon surface expands into a surrounding three-dimensional room. The universe does not require ordinary space outside itself into which it expands. Its internal distances can change without embedding the cosmos in a higher dimensional external room. General relativity describes this intrinsically. Again, geometry can be understood from within. No outside viewpoint is required. This leads to one of the most common questions. Where did the Big Bang happen? In the standard cosmological model, the answer is not one particular point in today's space. The early hot dense state existed everywhere in the observable universe. The Big Bang is not an explosion that begins at one location and throws matter into empty surroundings. It is an early state in which the scale of cosmic distances is much smaller. As time passes, the universe expands. Every sufficiently large region participates. If the expansion is run backward mathematically, average density and temperature increase. Galaxies approach one another. The universe becomes hotter, denser, and more uniform. Continue far enough backward, and the classical equations eventually approach conditions where our current description becomes incomplete. The phrase Big Bang often refers to this hot, early evolution. It should not necessarily be imagined as a tiny fireball sitting in darkness. The universe does not explode into space. Space itself participates in the evolution. To describe a homogeneous and isotropic universe, cosmologists use a family of geometries associated with Friedmann, Lemaitre, Robertson, and Walker. These are commonly called FLRLW metrics. The assumptions are simple on very large scales. Homogeneity means the universe is approximately similar from place to place when viewed on sufficiently large scales. Isotropy means it looks approximately the same in every direction. Locally, the universe is obviously not homogeneous. There are planets. The gravitational waves can keep moving silently across the cosmos, and spacetime can continue doing what it has always done, curving, expanding, carrying light, and measuring every journey in its own quiet way. You do not need to travel any farther tonight. Let the distances become softer. Let the clocks become quiet. Let the strange geometry fade gently into the dark. You have gone far enough for one night. And if you are still awake and would like to keep drifting, another quiet journey can simply continue on screen. If these calm nights bring you a little peace, you are always welcome to return to Nightfall Science and wander gently through the universe again. Sleep well and good night.